And welcome back. This week we're going to talk about mechanisms and a little bit about motion. So there are hundreds and thousands of mechanisms that human beings have come up with to turn the kind of motion we have into the kind of motion we want. Might be as simple as this. You're turning rotary motion of the door handle into a linear back and forwards motion of the striker bar here. Barrel, I think it's called. Same thing happens with a deadbolt. Rotary motion at one end, linear motion at the bolt itself. That could also be the same thing if you ride a bicycle. There are a ton of different mechanisms involved there. This is a side pull brake. And every time you drive a car, there are possibly hundreds of different mechanisms in the car, from the door handle to get you in, the electric window going up and down. If you're lucky enough to have electric seats, this, for example, is a seat actuator, turns rotary motion from the electric motor via a worm gear into a lead screw turning around, but going much more slowly and with a lot more force than this motor was turning. So that's a very common mechanism. Or windscreen wipers, turning the rotary motion of an electric motor into a back and forth oscillating motion. And if you're old-fashioned enough to have an internal combustion engine vehicle, there are probably 65, 70, 80, 100, 250 different mechanisms underneath the hood of the car. There are gear sets, planetary gear sets, sliding yokes with gears and selectors. There's air compressors, there's belts, there's drives, there's solenoid valves. There's a whole mess of stuff going on there. If you have a more modern car, an electric car, there are less parts in the motor, but there are still windscreen wipers, door handles, brakes, hydraulics, air conditioning, a whole host of things going on there. So everywhere you go, take a look at stuff and see if you can see the mechanism behind it that makes it work the way that you need it to work. And to do effects, we need to take the motion we have again and turn it into the motion we want. So we need the means to manipulate motion. And I'm going to get a t-shirt with that written on. You can buy it at my Etsy shop. Let's look in a little bit more detail. First, we're going to start with gears and pulleys. First, gears. I'd just like to point out these are not gears. These are actually part of a globe building project, but they all illustrate my point fairly well. Basically having teeth that intermesh and transmit motion from normally a larger to a smaller or a smaller to a larger. If we look at this, you see I've marked these very expertly. If we turn the small one a full revolution, the large one's only done three quarters of a revolution. So in fact, this is being geared down. If we spin the larger wheel, again, if we spin the larger wheel, the smaller wheel will go around one and about 1.5 times. So that's the gearing up, making the driven wheel go faster than the driving wheel. It's very important, and if we were to use an even bigger gear, again, this is not a gear, this is just a shape that looks like a gear. If we were to replace the large wheel with an even larger one, then we'd be either gearing up or gearing down to a much greater extent. And if you pack all those little gears into a box, it becomes, guess what, a gearbox. This is the motor and gearbox transmission out of one of those kiddies Barbie Jeeps that you see tootling down the street. And what it allows you to do is take a very small motor that spins very fast, gear it down through 1, 2, 3, 4, 5 different gear reductions. So you get the final drive going quite slowly but quite forcefully. That way you don't need a very big motor, and motors cost money. So if we speed this up, you'll hear how fast it's going. It's not a very well built gearbox. Some of these gears are made of plastic. So that's about full speed. But it is quite hard to slow down. And if you want to get, this came from American Science and Surplus for the grand price of $12.50. Pretty good value. But if you're in the more industrial world, you would end up with something that would look a bit more like this, more neatly packaged. And again, this is full speed. I don't know if you can see how fast that's moving. All I can say is it's not very fast. That's flat out. But it's providing a lot of torque for a very small motor. I think also this is a 24 volt motor and I'm running it on 12 volts, so it would go a little bit faster. So there are also planetary gear sets if you want to reduce your speed even more. Whoa, I'm going to spill these. These came out of a Makita. You can see this, they all spin around. The one in the middle is called the sun gear, and then the planets around the outside, just like the solar system. These things, when you take them apart, good luck getting them back together again. There are a lot of very small parts that only fit in one very exact way. So that's straight cut gears. Well, actually, these would be called spur gears. If they had a more fanciful angle on the teeth, they would be helical gears. And there's reasons for doing that that go towards efficiency and smoothness and longevity. Let's moving on. So if you would like to change the direction of your motion from this away to that away, you're probably going to need some bevel gears. This is a right-angled drill attachment, and if we remove the case, we can see here it has a set of beveled gears, and one of them is bigger than the other. One of them is exactly twice the number of teeth than the other, so you can swap which side the chuck goes on, so you can have either twice the speed or twice the force. And these are very simple bevel cut gears and give you a nice 90 degree, reasonably efficient, fairly cheap version, that one. If you want to go a little bit fancier, this is a right-angled drill, not quite right angled, but very close to it, that I managed to destroy quite effectively. And if we look inside, you can see there's the motor down here in the handle where all the weight is. The motion gets transferred up this shaft into a right-angled gearbox and then to the chuck. And if we look inside the gearbox, we can see, just about, you can see these are spiral or helical cut gears. Pardon me if I'm getting that wrong. They give a much more efficient transfer of power. The reason why the chuck end here isn't moving is because I used this to drive a bolt, and the planetary gear set that is here that does another final gear reduction got destroyed in the process. So this is toast. I think it cost me $80, and I think it came from Harbor Freight, so it was kind of toast already. But this is the same process that will happen without the planetary gears in an angle grinder. Again, we have the motion, the axis of the motor is spinning like this, and it comes to here, and then there is a set of beveled gears, so it will drive it 90 degrees into this kind of motion. And again, it will gear it down. So the motor is probably doing 30,000 RPM, and the end result might be 10 or 12,000 RPM. So those are beveled gears. If you took one of our pairs of gears here and you unwound it, literally peeled all the teeth off and laid them out flat, you would end up with a rack and pinion. This would be the rack and this would be the pinion. It may sound familiar to you because it's how a lot of steering works in modern cars. You turn the wheel, which is the pinion, and the rack goes backwards and forwards and is attached, where's my hands, is attached to the wheels with a rod, and the rod goes back and forwards and the wheels pivot on their bearings. So rack and pinion, very useful way to turn rotary motion into linear motion or vice versa. So another very useful way of transmitting motion is to use pulleys and belts. Preference is normally to use a toothed belt, that way they don't slip and you can get a positive engagement and drive a lot more power through the belt. And just like our gear set here, if one of the gears is bigger than one of the cogs is bigger than the other cogs, pulleys, gears, you either increase or decrease the speed, either increase or decrease the amount of torque going through the system depending on which wheel is driven. So for this is a 36 tooth pulley. This is an 18 tooth pulley, so they are a 2 to 1. So again, if our marks are both facing each other, if I drive the large wheel, you'll see that right now this has done a full 360, this has only done 180 degrees. So if we drive this wheel, this goes twice as fast. If we drive this wheel, this goes twice as slow, but with twice as much power, twice as much torque, twisting force. Other interesting thing about belts, the difference between belts and pulleys and cogs is that when I rotate these two, they're going in opposite directions. Always, they have to. If I rotate these, they're going in the same direction. This may matter or may not matter to you, but it's always worth bearing in mind. What's next? Worm gears. You can always tell a worm gear because it'll look like this. It doesn't look like a worm. It has a shaft coming out with, well, let me describe it more simply using a diagram. This is the worm and this is the gear. So this does the driving. The motor is like this, spinning this way. And for every time that this worm goes round once, full 360 degrees, this cog here goes round 1 tooth's worth. So this has 25 teeth. So this right now is 25 to 1. Pardon me. So it's a very, very good way of getting a lot of gear reduction. So if you add these to each other, if you put another set of worm gears after this, you'd get 625 to 1. So this would go around 625 times. It would go from this to another worm gear, and it would go round once for every 625 times this went round. If you added another set, you'd get 15,000 to 1. And added another set, you'd get, it's written on the back, I'm cheating, 390,625. If you had put 4 of these together, you get incredible reduction. The other bonus to this is that because this is like a threaded bolt, it's what's called self-locking or self-braking. You cannot rotate this and make this move. You can only make this move first, which will cause this to move. So it's very useful in situations where you're hoisting or lifting, because the moment the motor stops moving, it acts as a brake. So that's worm drive. And we're back just briefly again on worm drives. It's worth noting this is a electric window operator. This is a windscreen wiper motor, but we're going to look inside the guts of this a little bit later. But anytime you need very high torque and you don't mind low speed, that's where you'll see this classic arrangement of the worm at the top and the cog underneath. This is another one from an industrial application. It's got the same thing. Again, you can see the worm here going this way, and then the output shaft going around that way, and it'll go very slowly, but nothing will stop it. Next, now pulleys and gears are pretty good at changing the speed or the force of the motion or transmitting it over distances, but what they're not good at doing is transforming it from one form into another. So let's say you start with rotary but you want linear, or you start with linear and you want rotary. There are tens of thousands of very intricate little mechanisms that have been come up with over the years to turn any kind of motion into any kind of other motion. So let's have a look at a few of those. First off, the crank slider. Sounds cool, huh? Well, not very. I'm too lazy to make one, so here's an example of one. You may think it looks familiar because it's the basis of pretty much every internal combustion engine apart from a Wankel, and you also may have seen this on the outside of a steam train. Pardon me. So it basically turns this rotary, this is not working for me at all, turns this rotary motion into a back and forth reciprocating motion, or the other way around in the case of an internal combustion engine, that this is the piston, I can't, no, yeah, bang, bang, it's a two-stroke, and turning it into something we can use, which is basically the motion of a wheel, which is what we want. So that's a crank slider. So this is a bell crank. So named because it was used to ring bells in the servants' quarters when a rope was pulled. And you can see it has a fixed pivot point and two moving pivot points, and it changes to the direction of the motion from vertical to horizontal or vice versa. And by moving the pivot points, we can change how much work is being done. So now we have a lot of movement here and not much movement here, but more force here. And we could obviously drive the other way. We could have a little bit of movement and a lot of movement on this one. The bell clank. This is a reverse motion linkage. Again, these are all very, very simple. These are merely to wet your whistle so you can do more research, use the resources below to investigate. So in this case, if this one goes this way, this one goes the other way. It's a very simple reversing mechanism. Again, it has one fixed pivot and two moving pivots. And you can compound this. You can change the relationship between. Effectively, we're changing the gearing now. So now this bottom one moves a lot, and the top one, this being the top, moves only a little bit, but with more force, probably with about twice as much force. And again, you can reverse this so that your driven one is moving a little bit, your driving one is moving a little bit, and the driven one is moving a lot. What's up next? So, several of the things we've talked about so far are described in one unit. This is the windshield wiper from a 1979 FJ40 Land Cruiser, mine I might add, and we can see it working. You can see it has a motor here which is spinning like this. We apply 12 volts to it and somehow we end up with this mechanism. We also end up with another mechanism because it has two wipers. Coming out of this end is a cable which goes in time with this guy. I just put the pin on here so you can see it moving. I've used this for a number of things, most of which were not related to windshield wiping. Okay, actually we can leave that running. So what we can do is have a look inside and see what trickery is going on inside here. Isn't that pretty? So, you may not be able to see this because it's way down in there, but first off we have a worm drive. This motor is got a shaft coming out like this that is spinning around. It is rubbing on the side of that small gear here, which is going reasonably fast. In a worm drive there's a worm on the shaft of the motor and the cog is right here. Then it goes to a gear reduction from small to large. So this is going probably 4 times. This is going 4 times as fast as this is. And then we end up with a crank slider mechanism because we want the back and forth motion. And that gives us here, you can just about see that. You can see there's a rack and pinion because on the back of here is the pinion. So this in here is the rack. This is the pinion. So when we put them all together, we get the right speed at the right motion going the right way. And again, that's a rack and pin, worm drive to a spur gear reduction to a crank slider to a rack and pinion. And then to an armature on the end, which is the windscreen wiper arm itself. And the other windscreen wiper screws into the end of the rack here. So it uses like a very thick brake cable coming out the end to transmit motion in a very similar manner to the other windscreen wiper, which is over that away. So I think this is one of my favorite examples of how you can jam a whole bunch of things into a metal case and it'd be very reliable. This is a true gearbox. And despite all my abuse, it still works. So here is another mechanism I've been too lazy to make myself, a cam and follower setup. You can look in the resources below where there'll be some examples of that, probably to this very page in fact. This could either be, could have a valve on it, as in a camshaft for an internal combustion engine, which would operate all the intake and exhaust valves, or this could be a switch which operates some other electrical piece of equipment. These cams come in many different profiles depending exactly upon what they're needed to do. Again, look in the resources, it'll show you all the different kinds. Very easy to make yourself, to make puppetry or automata. We're not done yet, not by a long chalk. So another way to turn rotary motion into linear motion, i.e. this from this, is to use what's called a lead screw. A brand name you may be familiar with or not is the Acme thread. Basically what it means is it's very coarse thread. So normally a 1/4 bolt means that it's a 1/4 of an inch thick and it has 20 threads per inch. A Acme screw like this, I don't know how many it has per inch, but it's not very many. The end result is, if you turn it even a little bit, the nut, this is the nut, zooms along. And you can get a variety of different twists to it, so they're called either fast or slow. And instead of having a drill here, if you put a stepper motor and you attach that to a laptop with a driver, you can get precise, repeatable motion control for cheap. Works very well. There's another kind of lead screw. This is made by Rolex. This is called a Zero Max because it has zero backlash. You can, because it has no teeth, this is just a standard 1/2 inch hardened steel rod, but there are angled bearings at each end of this block that squeeze down onto the shaft, and as a result you can get this to happen. But obviously what's more likely to be happening is this stays still and you drive it backward and forwards by putting a stepper motor on here, encoding the signal, and then you can repeatedly say go to exactly where you want it to go, stop, move at the speed you want it, and again repeatability for motion control systems, and you can link them up with cameras, motion controlling cameras, so the whole thing can all work together. So that's lead screws. Again, Acme screws, what they're mainly called, but that's a trademark, so don't sue me. This is also very commonly used on 3D printer, CNC machines, routers, that kind of thing, because it gives very precise control. So, levers. About 2,250 years ago, Archimedes, the famous Greek mathematician, inventor, all-round bon vivant and good guy, said that, give me a lever and a fulcrum to put it upon and I will move the world. Actually, he said, give me a lever long enough and a fulcrum to put it on, I'll move the world. Which is, relatively speaking, actually true. So, there are 3 kinds of levers, first, second and third class. And the only difference between them, apart from the extra legroom and better food you get in first class, is how much use and how much mechanical advantage we get from them. So, from the beginning, this is our load, it's about 5 pounds of steel. This is our fulcrum, pivot point, and my hand is going to be the force. So this is a first class lever, which means the fulcrum or pivot is between the force and the load here. So it's very useful. Very commonly, you've probably seen this as a seesaw. But we can adjust by moving the pivot point how much work we get out of it or how much work we put into it. So right now, with the weight very close to the fulcrum, I can balance this probably 5 pounds of steel with the weight of a cordless mouse, which is probably 3 ounces. But if we go all the way to the other end, if I want to lift that now, I'm going to have to put in 20 or 30 pounds of force to get that off the ground. So very useful. It's also very useful because the motion of the load is opposite to the motion of the force. So we have gravity. If you want to jump on this end, gravity will help you, and quite often we want to lift things. So it's all round first class lever. Now we're back to second class seats on the train, in which the load is now on the same side of the fulcrum as the force is. And we can move the load backwards and forwards, but we can never move it past our force. So my hand is always moving more than the load is. And we can obviously make it easier for ourselves, but we get less movement down here. The other thing to note here is that the force and the load always move in the same direction, as opposed to the first class lever where they move in opposite directions. Now they're moving in the same direction. Now let's scrape the barrel. Third class lever. Third class lever means both the load and the force are on one side of the fulcrum, but now the force is here. So I am lifting at some great disadvantage. Of course, this is not a zero, it is a zero-sum game. So what we gain by that is, if we put something very light here, I can throw it very fast. Whereas I won't be able to here unless I do the same thing. But again, this is what your bicep looks like. If you can imagine, the fulcrum there is my elbow, and the muscle comes down on this side. So the muscle is attached to my forearm here, and I'm not going to be able to lift that up. And then elbow, and then the force is lifting up is my bicep. Imagine this hand is my bicep pulling up. So your bicep is a third class lever. Sorry about that. So that has been merely a tiny sampling of the huge number of widgets there are out there, transforming motion and forms of motion from one kind into another for our benefits. So while you're out there interacting with this stuff every day, try and understand what's behind the outer surface, what's going on, what linkages and leverages and gears are going on behind the outside. Understand it, learn it, use it to your advantage later. Yeah, I mean, for example, we never got to solenoids. This is a solenoid, electrical solenoid. You apply 12 volts to it, it pulls back a pin, it's got a spring, so it springs back. Didn't have time to get to that. But we're going to keep doing this, so check back with us later. Maybe we'll fill you in. Until then, thanks and goodbye.